Okay, in the previous two videos, we created a Verilog module, created an IP using the Verilog module. We then created a hardware design using the Jink and our IP. And now we're working on the software component of our design. So after creating the bitstream, we exported the hardware and we launched SDK. So that's where we left off. So here's our Xilinx SDK. When you export hardware and launch SDK, whenever you have a new IP that you create yourself, SDK creates drivers for those. So here are my drivers. If I look at my, if I expand the design that I created, here are my drivers. If I open the H file, the header file for my IP adder 8-bit, that's the adder I had created, it has a memory write and a memory read from a register, as well as code to do a self-test. If you want to see what the self-test does, open up self-test. What it basically does, it writes to the first 4 addresses after the base address and reads back those what it wrote, and basically verifies that whatever it wrote is what it's reading back. Okay, so you can do a quick self-test on your own register and so forth. In this case, we'll worry about that later, but let's create a new software application. So let's create an application project. I'm going to call it my adders as software. Make sure it creates a board support package. It's standalone and it's using the hardware platform that we had just created. In this case, I'm going to use an empty application. So hit finish. Now here is the board support package for that application as well as the application source. Under the source, let's go ahead and say new file. I'm going to create a new C file. So let me call that main.c and hit finish. So here is where I write the software code. So let's start with basically the header files. So the major header files that we're going to need are xparameters.h. xparameters.h, so that we include everything that we had done in the design. We're going to deal with some of the IOs, so I'm going to include Xilinx IO. We're going to use different types like U32, U8. So I'm also going to include basic type. Okay. And if we need to include more, we'll come back and add that later. But let's start with our main code. We'll call it int main and we'll return a 0 at the end. So right here, let me start out by creating a Xilinx printf statement, so now we know what we're doing. So let's say start up my IP adder. It's not 32, it's an 8-bit test. What I want to do is, now we have 2 numbers. Let's say we want to add 2 numbers. A is, let's call it 1. To make it easy, B equals 3. Let's test this out. To do that, we need to write to the slave register. We need to figure out where that slave register is. The way to figure that out is to click on xparameters.h. If you hit the control key and use your mouse, xparameters.h just became a hyperlink. Clicking on that takes you to there. So here, let's go and find our IP. I'm going to quickly search for adder, and here's my adder IP. That's the device ID of my adder. Here's the base address. This is what I'm interested in. This is the base address of my slave register 0. You can also look at what the slave register 1 offset is from that base address. Since slave register 0 is 32 bits and the memory here is byte addressable, that means the base address of slave register 1 is 32 bits away from this, so it would be +4. the offset will be +4. You can find that out by clicking on my IP adder 8-bit driver it created, and here are the offsets for the 4 slave registers that we have in the design. We're not going to need more than the 2, but by default the minimum number of registers the AXI Lite has is 4. So slave register 0 is where our inputs will go, the bottom 16 bits. Slave register 1 will contain the output sum in our case. So I'm going to go back to my main.c. That's the base address of my of my slave register 0. So what I want to do is do a write from the PS to that. So I'm going to use Xilinx out 32. I'm going to write 32 bits to that particular base address, and what I'm going to write is basically 0103. So actually this should be 0301. That's A, that's B. Okay, and the top 4 bits are basically 0000, the top 4 hexadecimal digits. So that's my 32 bits right there. So that's what I wrote. This will place this value on the base address. Base address belongs to slave register 0. The bottom 8 bits belong to A, so that's 1. The top next 2 bits belong to B, so that's 3 in hex. So 3 in hex plus 1 in hex should be equal to 4 in hex, and we should be able to verify that address. How do you verify that out? Let's create a U32 variable, unsigned 32-bit variable called adder out. And what we'll do is adder out equals we'll basically do read the 32-bit from a particular address. So that's where we put in the address, and our address is basically the base address plus an offset of 4 to be able to read that. Okay. All right. So we want to find out what these values are. So let's do a Xilinx printf statement. Let's print out. Let's say what is our value? A is 1. B is equal to 3, and sum should be equal to, I'm going to print that out in decimal, so percent is D, and then that should basically take care of that, and we'll call this adder comma adder out. Here's a simple addition of 1 plus 3. Just to make sure we're getting the correct result, let's do one more addition, and this time make it a little more higher number. So I'll call it FF. So FF should be 255 in decimal, and let's make A equal to 13. So 255 in decimal plus 13 in hex is equal to 19 decimal, and we'll find out what the results are. Okay, so this one is 19 in decimal and 255 in decimal, and then we'll find out what the sum is. Save this. Before we can download this code, we need to make sure that we add the bitstream to the FPGA. So let's click on turn on my board. So for this part, you'll need the board to be connected. So I just powered on my board. Bitstream program. Make sure you have the right bitstream. So it's programming. Now, one thing I want to do is set up the terminal so that I can verify the results before I download the code to it. So serial terminal COM6 115200. Say OK. My terminal is connected. Now what I want to do is basically download. Right click on that, run as launch on hardware, and wait for it to finish. Okay, So here it is. We're done. 1 plus 3 is 4. 19 in decimal plus 255 in decimal equals 274. So we created an adder that works perfectly. So that is how you write the software. Now in this case, we wrote our design using Xilinx In32 and Xilinx Out32. This is my personal preference. However, let's go back and look at the header file. In the header file, we had two functions or two macros defined. My adder IP write res basically calls Xilinx Out32. And my IP address memory read register, which basically takes in the base address and the register offset, basically does exactly what we did with the Xilinx In32. So you feel free to use this or this or a different way of calling memory locations. So that is the software design for our adder.